So we have a lecture devoted to probabilistic Bayesian numerics by Mark Girolami from Cambridge. Please.
Can everybody hear me okay? So it's a shame that it's 5:30 in the evening. You must be tired after a whole week of lectures and probably some late nights as well, I'm sure. So I've got to try and keep you interested for the next 90 minutes or so. So what I'm going to try and do is not pack as much in to this lecture as I possibly can, but I hope to be able to motivate a change of thinking as far as numerical procedures are concerned. And I would welcome interruptions and questions from the floor. So I'm going to try and take these things a bit more gently. And as I said, if I rush over things and you want some clarification, then just shout. So the first thing is, what is this whole thing, probabilistic numerical computation? It's certainly something that is central to machine learning, but it's also central to applied mathematics, to engineering applications, and to statistical applications as well. And it really is quite a revolutionary way of thinking about numerical computation, and therefore the design of algorithms and methods to numerically solve particular problems. This doesn't work. That's a good start. Okay, I've put up some of my collaborators in the research program of probabilistic numerics, and what you should be able to see is that there are some key people from machine learning: Philip Hennig, Mike Osborne, Dino from Oxford. They are core machine learning research experts who are trying to drive the probabilistic numerical message home as far as machine learning is concerned. But if I look, there are also some very serious and very senior mathematicians: Andrew Stewart from California Institute of Technology, Tim Sullivan from the Free University of Berlin. These are analysts, both stochastic analysts and numerical analysts, and they have accepted the fact that numerical computation can be seen as a statistical inference problem, and therefore the design of methodology in problems can be embedded within a statistical framework. And so it's very exciting to be working with some very senior mathematicians. I have to say that not all mathematicians accept this viewpoint. And then the other three are previous postdocs and PhDs of mine who are statisticians. So the one thing that you really notice about probabilistic numerical computation is that it inhabits a nexus between applied mathematics, stochastic analysis, numerical analysis, statistics, mathematical statistics, non-parametric statistics, computational statistics, and machine learning with applications in, for example, Bayesian optimization and Bayesian quadrature and so on. So a very exciting area of research to be working in. This is going to annoy me. So, probabilistic numerical computation. So what is it? And I'm going to take you back to school. And you've probably all solved this equation. We have some function u It's a function of t, let's call it time. And we know that the rate of change of the function u with respect to time is equal to the value of the function scaled by some parameter theta. And we also know that the initial value at t equals 0, in this case, is equal to 1. Now, what's the solution? What does u of t equal? Right, where's all the machine learning experts that have forgotten Mathematics 101? It's the exponential of theta multiplied by t. So every schoolboy and schoolgirl knows this solution. But the important thing is that it's a reasonable model for things like bacterial growth. It's a reasonable model for radioactive decay, compound interest in finance, and so forth. Now, the key point here is that although the function u of t, given theta, is implicitly defined, so we have this function definition, but the function itself is hidden within the differential equation, right? And so what we have to do is use some mathematical analysis to obtain what the functional representation of u is that satisfies the differential equation and the initial conditions. The point is that this is a fully deterministic object. If we know the value of the function at time equals 0, then we know the value that the function will take at any point in time thereafter. And so we have this deterministic way that something will decay, or this way that something will grow. It will grow in a deterministic manner, in a Newtonian kind of clockwork manner. It is completely determined. It is completely deterministic. So, given this initial value, any point in the future, the value of the function is completely determined. There is no uncertainty, there is no randomness, there is no stochasticity. Now then, let's just look at this and think about this a little bit more carefully. The rate parameter theta, this actually may have been something, and typically is, something that has been empirically derived from observations by making experiments, making measurements, and then deriving what that rate parameter happens to be. Now, as soon as that is the case, as soon as that rate parameter is empirically derived, it immediately introduces a notion of uncertainty into our deterministic world. And so what it means is that the clockwork decay or growth of our exponential of t times theta is now no longer completely determined because we are uncertain about what the value of theta may be. Okay? Now this is the crucial point here. Right? So theta, if we empirically derive it from measurement, then there will be uncertainty associated with the value that this parameter will take. So it's not as if nature handed us the value of theta for the radioactive decay of whatever it happens to be. Now, how do we deal with this uncertainty? Well, we can ignore it. Or we can use schoolboy probability to describe our uncertainty in the parameter theta and the subsequent propagation of that uncertainty into our function u of t given theta. So if for example, we have some measuring device that gives us the value of theta given some measurements that we make, and our measuring device has some level of precision, then clearly there is going to be a measurement error. And the age-old representation of standard errors in measurement has typically been the normal distribution. The errors in measurement will typically follow the Gaussian law or the normal distribution. And so if we were to make measurements about the rate of decay of, or the rate of growth of some bacteria that we happen to be studying in a Petri dish, and we find that the error associated with that value is normally distributed and it has some precision, which is defined by a standard deviation sigma. And theta will then, of course, have a mean value. So now we have distributional properties associated with theta, and the push forward of that uncertainty in theta into the function that satisfies the differential equation and the initial conditions now turns out that a probability distribution is induced over our function that solves the differential equation. And it turns out, and again, it's a very simple schoolboy, schoolgirl, okay, maybe not school, yeah, probably schoolboy, schoolgirl problem to show that if theta is distributed normally with a mean of mu and a standard deviation of sigma, then the exponential of theta times t is now going to be log normally distributed with a location parameter which is going to be equal to mu t and a scale parameter which is going to be equal to sigma t. And so what this means is that the growth function, the mean value of the growth function is now going to be equal to the exponential of mu times t plus a half of sigma times t. And the standard deviation, or the other higher order moments, would be defined by some function of the location and the scale parameter. The point is that if we have a growth curve, it is now no longer a deterministic object. We could draw samples at every time point and get different realizations of what that growth would look like. And so that uncertainty in our definition of theta has now changed the very nature of the function which satisfies our differential equation from a fully deterministic object to one which is now probabilistic. The definition and the description of the solution of this simple differential equation is now a probabilistic object described by this log normal distribution. And this is a fundamental change. Now again, if anyone disagrees or anyone has any questions or doesn't quite see that, then please just shout. I know that it's now 6:15. You're probably thinking about your dinner and your beer, but stay with me for about another hour or so. Okay, if we've bought that uncertainty in that parameter, now transforms a deterministic object into a probabilistic object, let's think about this a little bit more. We said that uncertainty can enter due to the parameterization of the PDE. But what if we had a more sophisticated differential equation, one which we couldn't analytically solve, one which we had to resort to numerical methods, to approximate numerical methods, deterministic approximate numerical methods? What then? What would happen then? Well, let's just take this same example and just work through it a little bit more. So now what we're doing is we're moving away from having an analytic solution to one where we don't have an analytic solution, but we can get an approximate solution by resorting to numerical methods. As Donald Rumsfeld once said, our implicit function u of x, or u of t given theta, is now a known unknown. We know that we don't know what it is. So if we then move to the more general case where we have a nonlinear differential equation, so u dot just represents du by dt in this case, and f is going to be some nonlinear function of the solution u, given whatever the parameters happen to be. And so the most simple numerical method that we can think of would be the forward Euler method. Now, typically, we would never use the forward Euler method because it's not necessarily stable. We would probably use a backward Euler method or a Crank-Nicholson or some other numerical method. But just for the purposes of making the point clear so that we can follow the argument, let's just look at Euler's method. Now, how many of you are familiar with Euler's method? Or how many of you remember taking lectures on Euler's method? So a couple of rows. Everybody. Okay, so we know that with Euler's method we take, let's just say that we're working with one-dimensional time. We split it up into potentially non-equal discrete elements or sections, and at each discrete time point n, we would get an approximation of the solution, and we use capital U sub n to denote the approximate solution at discrete time point n, and the solution at time point n plus 1, discrete time point n plus 1, is simply just the sum of the approximate solution at time point n plus h, where h is going to be the spacing, right, or the time difference between time point n and time point n plus 1, and the value of the right-hand side of the differential equation, where we now plug in the approximate solution at time point un. And we just keep on iterating that from time point 0 to whatever the ultimate time point would happen to be. Right, let's go back to our simple schoolboy example. And so remember, the schoolboy example is just du by dt equals, what does it equal? Theta u. And in this case, we're going to say that we know what the initial condition is, and we just set the approximate initial condition to 1. And it doesn't take much effort to see that u at n plus 1 equals u at n plus h, the time step, theta, and then u of n. And that, in essence, tells us that at any time point, any discrete time point, n plus 1, then the deterministic numerical approximation is just going to be 1 plus h to the theta raised to the power of n. This is a completely deterministic numerical method to solve this differential equation. There's nothing stochastic in it, nothing random in it. But let's just remember now that uncertainty has entered into the numerical procedure because of theta being empirically derived. So we have some uncertainty associated with theta. Now, in this case, let's say we know a little bit more about theta. So we know that it's strictly positive, and its distributional characteristics are log normal, again with a location mu and a scale parameter sigma. It then turns out that the mean value of the approximation at each time step n and the corresponding second moment looks something like this. So we have this summation of all of the kth order moments for theta, and these are weighted by the discrete time step from the numerical procedure, and then these binomial coefficients. Now, the point to take away from this example here is that although we have a deterministic numerical procedure, it actually contributes further to the uncertainty in the solution because of our uncertainty in theta. So it compounds our uncertainty in the forward predictions that we would make. So we're no longer deterministically stepping forward in time. We are now making probabilistic predictions in time. And the deterministic numerical procedure has contributed to our uncertainty, right? So the statistical properties of the approximate solution. So in other words, the numerical procedure is actually, and arguably, and hopefully someone will argue with me, is now no longer a numerical procedure that's fully deterministic. It's actually a statistical inference procedure. We wish to infer the distributional properties of our unknown function as a function of time. Does everyone get that? Any questions? Good. You need to shout, I'm old and deaf. So it's always dangerous when a topologist is going to ask you a question. Yeah. Yeah. So in this example, what I'm saying is that I don't have a lot of information about theta. So the function could actually be growing or it could be decaying. I don't know which it is. And it made the math easier. In the other example, I then say, I know that the unknown function is going to be growing, so it's always going to have a positive value. So I can say that theta is log normally distributed. That's all. There's no, it's just really to, to make the point rather than anything else. But I maintain here that even Euler's method, deterministic Euler's method, without adding any stochasticity to it, then introduces additional uncertainty, and therefore one would be entitled to consider these numerical procedures as procedures associated with statistical inference. Right. Let's just go one step further. Now let's say that we have complete knowledge of the initial value. So we're still working with our little toy du by dt equals theta of u, theta u. So we know with absolute certainty what the initial value is. And furthermore, we know with absolute certainty the value of theta. Right? So nature has given its secrets away and told us what the decay or the growth rate happens to be. So the only thing that we don't know is the solution of the differential equation. Okay? And if we don't have an analytic solution, then we will resort to our deterministic numerical procedure. So let's just think about this. We have no uncertainty about the initial condition. There is no uncertainty about the rate parameter. The only thing that we don't know is the solution. But we have a deterministic procedure in Euler's method that will give us an approximation to that solution. Now what? Well, in this case, everything is fully deterministic in our computation. And in fact, the evolution of the error that we accumulate at each step in the numerical procedure is fully determined, and it follows a deterministic evolutionary equation, and there it is there. So the error at time step n plus 1 is equal to, well, whatever the error was at time step n, plus then we have our discrete time step value, and then we have, well, what's this? Well, this is the difference between our approximation and the actual function value, and then there are some other higher order residual terms that we don't need to worry about. The key point here is that there is nothing random in this evolution of the error. There's nothing random in the evolution of the approximate solution. So there's no stochasticity. So there's no probabilistic semantics required here. Or is there? Can anyone see a small fly landing in the ointment in this equation here? Now don't all shout at once. What is the problem that we've got here? What is the problem that a classical numerical analyst has with this deterministic evolution of error? We don't know the true solution. So although we can write this equation down, we can't actually compute it. So we don't know what it is. So we are uncertain about it. And so again, the whole notion of uncertainty, and therefore the calculus required to reason under uncertainty, which is the probabilistic calculus, has to be considered, even in this case here. So we cannot compute the deterministic error because we don't know what the true solution is, and we cannot compute its equation of evolution It is unknown. Now, numerical, the textbooks in numerical analysis will then start to look at bounds on what the errors will be, and show how these bounds actually will decay and at what rates they will decay. But at the end of the day, these are bounds. These are not actual values of the thing that we are writing here. And one solution to this impasse is to consider subjective probability. So the probability of Definetti, of Ramsey, of Jeffreys, of Berger, of Bernardo, Smith, the subjective Bayesian approach, that if we write something that we do not know, then we can represent that uncertainty using probabilistic arguments and the probabilistic calculus. And the whole point of this little introduction is that the fully deterministic numerical procedure can be represented as a probabilistic inference procedure. And in other words, what we are looking for are ways to define probability measures in the function space of solutions of whatever the differential equations happen to be. And that is the whole drive of probabilistic numerics. I've given the example here of solving a trivial differential equation. But that same argument can be made in linear algebra, so solving linear systems, solving partial differential equations, which is what I will focus on for the rest of this talk, and other numerical procedures. So, probabilistic numerical computation. So if someone stops you in the bar tonight and asks you to explain to them what probabilistic numerical computation is, how many of you could make a convincing argument to them? No one. That's not a good sign. How many would be happy just to sit there and listen to someone like myself make the convincing argument and nod your head and say, yeah, I agree with that? Okay, good. Let's move on. You can ask 2 questions if you want. So, I mean, one of the big things with solving, so the question is that there are well-defined ways of solving linear systems, and we can solve them to various orders of error, first order, second order, and so on. So, where would probabilistic numerics come in solving a linear system? Well, one of the big issues, right, in solving linear systems is defining a good preconditioner. And the preconditioner, of course, is something that we don't know, because typically in real problems, we can't look at what the spectral characteristics of the linear system is, because it's either too big or implicitly defined in some way. And so one can argue then, okay, how do we define good preconditioners? And a paper has just recently appeared, as it happens, in the journal Bayesian Analysis, which looks at exactly this problem. So it defines some methods, Kirchhoff's style procedures from a probabilistic perspective, a Bayesian perspective. And what you end up with then are two things, is being able to infer the preconditioning and to be able to infer the actual directions that the linear solver would be moving in. Yeah, so linear solvers, you're absolutely right. And it's exactly the same with these approaches that I've just mentioned here. The point is that you mentioned the largest or the smallest eigenvalue, right? Typically, we will not know what that is, because if we can get that, then we've basically solved it. You have uncertainty. Absolutely, and I mean, and that's the whole thing, is that I am not for 1 minute arguing that this approach is going to be useful in all cases. I'm not for 1 minute arguing ditch, over 2 centuries of numerical analysis and adopt this. It may well be that, and linear algebra is solving linear systems is a very good example. The uncertainty associated with numerics is probably completely swamped by all other sources of uncertainty, right, for it to be worth ignoring. But there are many examples, and I will show some in solving PDEs and inverse problems where that is not the case. But the point is that for every numerical procedure, you could reasonably argue for a probabilistic numerical procedure. Whether it would have any utility is another matter. But as you said, you need to know either what the preconditioner is, or if you want to define what the preconditioner is, or what the rate of convergence is going to be, you need to have some estimate of the eigenvalues. And as soon as you start estimating and putting bounds and things, you have this uncertainty. Now, whether that uncertainty is going to be significant in not the statistical sense, but in the sense that it is something that has to be accounted for as the computation goes along, is another question entirely. Yes? Could you speak up? I'm old. I can't, So the question is that there is an accumulation of what, sorry? Yeah, of floating point errors. And is this taking into account? Well, I'm actually going to specifically refer to the accumulation of floating point errors. What's actually very interesting is that floating point errors, at the time of Turing in the 40s and 50s, in the 60s, dealing with floating point errors and their accumulation was a big deal. And there were many statistical ways in which to deal with that. And then we got into very high levels of precision of computation, and that was never really a problem. Now, however, because of things like deep learning, we are moving back to mixed precision, to lower precision computation because of compute cost. And the notion of dealing with the accumulation of errors, numerical errors associated with loss of precision in computation is now rearing its head again. An awful lot of numerical analysts are turning to statistical approaches to deal with this. And I'll briefly mention that. But that's a good, yeah, another good point. Any other questions? What time is dinner? Okay, good. So, when did I start talking? Half 5? Yeah, so, okay. So, probabilistic numerical computation. We've made a case for it. We've discussed, some potential applications. And this leads on from the second question by Bernhard, is way back in the 60s, Hull had this paper where he considered probabilistic models to account for the propagation of round-off errors. And the key point of the paper was that the conclusions were that most of these probabilistic models were actually pretty good in terms of dealing with the propagation of round-off errors. And it turns out that there seems to be a renewed interest in the work of Hull and many of the early numerical analysts, or computational numerical analysts, because of the drive to go to mixed precision arithmetic in computation. And again, this is another angle or another viewpoint on probabilistic numerical computation. But there was probably a more fundamental series of papers which really started off, I guess, with Persi Diaconis from Stanford, or he was at Harvard at the time that he wrote his 1988 paper. How many of you are aware of Persi Diaconis? How many have seen him doing the coin flipping trick? Does everyone know about the coin flipping trick? So Persi Diaconis is a very famous mathematician who just happens to be a big fan and one of the forefathers of probabilistic numerical computation. But before he started his career as a Harvard mathematician, he was a magician. He ran away from home and became a magician and learned all these tricks. So whenever he gives a talk, he'll start the talk with some card tricks or some coin tricks. Very entertaining. But he has this trick where he can flip a coin, an ordinary coin, and it will always land heads. Of course, it's a trick. The way he flips it, the coin doesn't actually flip, it just wobbles, and he can control that. But one thing that he did is he commissioned some physicists at Stanford to build a machine that would flip a coin. And the machine was so precise that the initial conditions of the flip were very well controlled, so that you could run this machine for a year flipping coins, and it would always flip a coin heads or tails. And the point of the whole exercise was to ask the question, is a coin flip a random process or a deterministic process? So what is it? Is flipping a coin a deterministic scheme? Is it like our solution of our equation du by dt equals theta u? Or is it something inherently random? What's the answer? So let's just, before we jump to Is it a determinate? Is a coin flip deterministic, or is it random? Deterministic, random. Okay, so some people believe it's random. Why is it deterministic? Okay, so the coin flip just follows the laws of physics, right? Physical motion. And they're deterministic. So why do we see randomness in a coin flip? Right, now you can answer. Because you don't know what the initial conditions are never controlled, and you don't know what they are. And so your model to describe that uncertainty in the deterministic process, which is a Bernoulli, a binomial, okay? It's going to either land heads or tails with probability a half, is just simply that. It is a model describing the fact that there are things you don't know about that deterministic system. And that was the point that Diaconis was making, is that even in deterministic systems, we still have to deal with uncertainty, and the calculus of probability is the language that allows us to describe that uncertainty, our lack of complete knowledge. And it is exactly the same as in the little introductory example that I gave you. And so Diaconis, in 1988, he published this very nice paper which asked the question, should quadrature be considered as a Bayesian inference problem? And he gave some very nice examples. And then, a few years later, Tony O'Hagan published a series of papers, and very comprehensive papers, where he developed a fully Bayesian perspective on numerical quadrature. I'm assuming that you're all experts in Bayesian machine learning and Bayesian statistics after some of the lectures you've had. Okay, excellent. And then John Skilling. John Skilling was a physicist at Cambridge in the early 90s. And he then devised a Bayesian approach to solving differential equations, or ordinary differential equations in particular. And they all asked the question, is numerical computation a statistical inference problem? And they all answered yes, we believe it is, and focused on coin tossing, quadrature, Bayesian quadrature, solving nonlinear ODEs. And the case that I've made to you with a very, very trivial example is that numerical computation can indeed be viewed as a statistical inference procedure. Now, what's interesting is that none of those authors, and these are all very senior, very well, very well-renowned individuals, when they asked the question, should numerical analysis be considered as a statistical inference problem, none of them were aware of this paper by Mike Larkin, Gaussian measure in Hilbert space and applications to numerical analysis. And this was a paper that was published in the early 70s, and I don't think it was cited at all until myself and my group and people like Philip Hennig and Mike Osborne started to study probabilistic numerics. And I unearthed this paper, and I think most of its citations started around about 2016. It was a paper that was way ahead of its time. And in essence, he argued that numerical analysis is in fact a statistical procedure, and he then did the technical work of defining the loss, so the average case loss rather than the worst case loss, in the function space, in the Hilbert space, and then define the appropriate probability measure in which to compute the expectations that are required to define a probabilistic numerical method by defining Gaussian probability measure in the infinite dimensional Hilbert space. It's a fantastic paper, and I think it's a real shame that it was never given the credit that it was due in the late 60s and early 70s. But if you have any spare time, or this becomes an area of interest for you, I would thoroughly recommend that you read this paper. He basically did everything that Diaconis, O'Hagan, and Skilling did almost 20 years before. And it's absolutely superb. Now, the reason that I put this paper up is because the technical machinery required to do probabilistic numerics can be very sophisticated. So in terms of defining measure theory in infinite dimensional spaces, infinite dimensional function spaces, and defining the appropriate notion of a probability measure in a function space, it can become very technical. And some of our work has focused on these technical aspects. How many of you are experts in Gaussian processes? And if you've sat through, 4 hours of lectures at this summer school on Gaussian processes, then I assume that you will be experts. So did you have lectures on Gaussian processes? Oh, you didn't? Tomorrow? Okay, so this is the biggest sales pitch for the lectures that you're going to get tomorrow on Gaussian processes, is listen to that. Because all a Gaussian process is basically a representation of Gaussian measure, which is defined in an infinite dimensional function space, and its marginal in a finite dimensional space happens to be a multivariate Gaussian distribution, probability distribution, defined by a mean function and a covariance function, or a covariance operator. And so all of that machinery that you'll hear about tomorrow and on Friday is basically the methodological machinery that is deployed for probabilistic numerics. But as I said, some of the more technical aspects in terms of showing rates of convergence, and in the lecture that I give tomorrow, I'm going to show that probabilistic numerical methods can actually exceed the rates of convergence that Monte Carlo methods, so the 1 over root n rate of convergence, that can be exceeded for certain classes of functions and certain classes of probability measures for certain problems, and we'll discuss that in detail in subsequent lectures. Okay, so that's Mike Larkin, who's sadly no longer with us and can't really enjoy his success, late as it is. But, you know, what he says, and it's a really, really nice reference. So he says, look, the numerical analyst has to estimate a function from a limited amount of knowledge of its properties. And of course, this is an ill-posed problem, but the problem can be made well-posed in a variety of ways, which Anyway, but as a member, but an attractive approach is to regard the required function as a member of a linear space, so a Banach or a Hilbert space, on which a probability measure is constructed. And that's what he does, and that's in essence what we do in probabilistic numerical computation. But you'll hear all about Gaussian processes in the next couple of days. So, what is probabilistic numerics? Well, the definition is that probabilistic numerics provides a way to model the uncertainty associated with a function and enables us to propagate that probabilistic description of the error, of the uncertainty, through subsequent computations. And I hope that I'll show you that in some cases this can be very important, and in other cases it might not be important. But the point is that this viewpoint allows you to ask that question and ascertain whether it is or whether it isn't, and take the appropriate action. So what does it do? What does this ability to model functional uncertainty provide us with? Well, it provides probability measures over all the unknowns. The residuals will have certain types of structure, and that can be propagated, as I said, through later computations. And one example I will give you is of solving a forward problem and an inverse problem. Many of you are aware of what an inverse problem is. What's an inverse problem? Shout. Did you all hear that? No. So, in essence, think of computer vision. Okay? What you see is some kind of output, and what you want to infer is what the actual object was. Okay? So you want to infer the input, right? So you get output data, and from that output data, you want to infer something that you don't know, right? Like what is the actual image? And so I'm going to talk about a particular inverse problem and show how that, in fact, this can actually be quite important. I think the other thing that's quite interesting, and for those of you who are always looking for good ideas for your papers that you're going to submit to ICML or Numerix, then this is a really fertile ground to provide you with a way to design new algorithms, which is always a good thing for machine learning. But for those of us who actually take our models and go to people that make decisions or form policies within governments or within government departments, or people that are going to put money right down on a bet, right, if you're working in banks or finance, one of the key things about this is that it will safeguard against any unwarranted optimism as far as decision-making is concerned with regard to the models that we're dealing with. So that's what probabilistic numerics is all about. Philip Hennig from Tübingen, Mike Osborne from Oxford, and myself, we wrote a paper for the Royal Society proceedings, which we said was a call to arms for probabilistic numerical methods. And it's quite a nice, modern, up-to-date introduction to the whole notion of probabilistic numerics and dealing with uncertainty in computation. Right. Let's move on to differential equations, partial differential equations. Ones where there are no analytic solutions, where we have to resort to numerical methods. Now, whose the times are here? How long should I speak for? 30 minutes? Yep. Okay. Any questions? Are we all happy? You're all with the program? Okay. So I'm not going to bore you, but differential equations, partial differential equations, hugely important in just about every area that you can possibly think of. Here's an example of an aquifer, an oil aquifer. This is a commercial model, a finite element model used for to model an oil aquifer, a subsea aquifer. And this is described by nonlinear versions of Darcy's equations, partial differential equations, describing fluid, potentially multi-phase fluid flow through rock and so on. Described by PDEs that have to be numerically solved, and we probably have data associated with that, and we therefore need to solve inverse problems to infer what the porosity or conductivity or whatever the materials happen to be that the fluid is flowing through. So oil and gas, big deal. Even in the life sciences, how molecules are transported within the cell. Are they diffused? Are they advected? What are the mechanisms? This was actually a paper that we published in Science Signaling some time ago, where we took a series of differential equations that described the signaling kinetics of a particular pathway that regulates the cellular division and its subsequent development. And even in the social sciences, using partial differential equations to describe the way in which people move or people do things, and in this case, how they commit crime and so forth. So partial differential equations are really, really important, and as I said, extremely varied. Here's an example of Navier-Stokes equations, which are describing some simple fluid flow on a toroid. Of course, we never bump into toroids in real life, apart from the donuts that we eat. But it's a nice way of solving these PDEs. Now, you really need to have probably drunk about a bottle of wine and stare at these for maybe about half an hour or so, because what you will see is that each one of these is solving the same PDE with the same initial conditions, but the uncertainty associated with the numerics means that the convergence or the time evolution of these fluid flows will actually vary, and in some cases can vary quite dramatically. So this is an example of some work that we did using probabilistic numerical methods in solving Navier-Stokes equations. Okay, so I'm going to work through a probabilistic solution to a very standard partial differential equation. How many of you studied partial differential equations at one point or other in your life? Everyone. So you all know about elliptic partial differential equations, or at least you slept through a lecture that discussed them. So this little partial differential equation is the one that we're going to use to build up a probabilistic numerical approach to solving this partial differential equation. Now, what is it? Well, we've got the divergence operator, okay? The nabla dot is the divergence. kappa x is going to be a parameter, and it's a parameter that's associated with the spatial coordinate. So x is going to be, just imagine that we're in a 2D plane. Let's not bother about thinking in 3D. Right? So x is a coordinate in our 2D plane, and kappa of x is going to be some parameter associated with the PDE, and I'll describe what it is just shortly. And then nabla u of x is the gradient of the function that we're interested in. So u of x is our unknown, and it satisfies the partial differential equation that the divergence of kappa of x, a grad u of x, is equal to some function g of x, think of that as a forcing, in the domain, right? So in the actual spatial domain that we're interested in. And then on the boundary, we'll call that delta d, we're told that the function that we're interested in, the red function u of x, is going to take on a value b of x on that boundary. So we've got the partial differential equation, right? So the left-hand side has to satisfy the right-hand side in the domain, and the function itself is going to be equal to b of x on the boundary. And our job is to figure out what u is within D. And we're going to be given the function g. We're going to know what that is. We're going to be given the function kappa, which is think of it as a diffusion constant. And we're going to be given the boundary function b of x. So we know all of that, and all that we want to do is solve for u of x. And for a general domain, then u of x really can't be solved. For one dimensions and for simple two dimensions, we can get analytic solutions, but for a general sort of domain, then this is typically something that can't be solved analytically. And so the way that most partial differential solvers are used is that we use an approximation. So the finite element method, or the collocation method, would say that our approximation to our unknown function u of x, we'll call it u hat of x, is going to be a basis expansion where the basis functions phi of the coordinates x, right? And we would have a finite number of rows, n, so phi sub I would be our ith basis function, and they would all be weighted by some set of unknown weights, wi, and we would sum all of those together to get our approximation. Okay? So the finite element method, the phi of i's would be finite element meshes, similar to the ones that you saw in the deep learning tutorial just before this, where you would mesh up the domain into a discrete partition, or you could use some sort of radial basis or some other type of basis function and just plop them down in the domain itself. Now what we're going to do is we want to quantify the error associated with u hat for finite n, and we want to do it in a probabilistic manner. So we go back to coin tossing Persi, and it was quite funny if you read the paper, because he says, actually in the paper he says, you know, taking a Bayesian approach to numerical quadrature might sound nuts, That's the language he uses in the paper. But he then goes on to argue that, well, you know, there are Bayes or admissible probabilistic numerical procedures which would correspond to standard numerical procedures. And so we're going to do the exact same here. We're going to solve this PDE probabilistically. Now, in this case here, all that we're looking to do is solve for U. We're given everything else. And this is what's called the forward problem. We want to solve the forward problem. But the inverse problem would be that we make some measurements, we gather some data for U of X, and we want to use that data to infer something that is unknown. Maybe we don't know what B is, but in most cases we typically wouldn't know what kappa is. And so the inverse problem that we're going to focus on is inferring what kappa of X will be, given data, so given observations. Now, this simple equation, it's a simple steady-state PDE. It describes a number of physical phenomena. Electrical impedance tomography is one example, and I'll show you quite a big application of that later on. Here's another example. What's the steady-state flow of heat? What's the distribution of temperature in a particular body, say in a metal heat sink, in the steady state? And so in this case here, the kappa X would be the thermal conductivity of the material that we happen to be interested in. So lots of examples. So how would we solve the inverse problem if we were Bayesian, which I'm assuming we all are at the moment anyway? Well, the first thing that we would do is we would identify the statistical object of interest, which is kappa of X. Now, if I did this, if I presented this more formally, kappa of X is actually a function in a Hilbert space. But I'm not going to present this formally because it will probably send you all to sleep. So I'm going to be a little bit informal, but just keep in the back of your mind that there's a whole load of machinery behind all of this. So what we're going to say is that kappa is going to have a prior distribution, pi of kappa. Right? So we define our prior distribution on the function kappa before we make any measurements. And it turns out that that prior will be Gaussian measure. And there are very technical reasons for that. One is because Gaussian measure in Hilbert space is well defined. And there's a whole host of other technicalities which I can bore you with, but I don't think you want to be bored with it. But that will be a Gaussian process. So by the time you've sat through your Gaussian process lectures, you'll be seeing Gaussian processes everywhere you turn. So we're going to say that kappa is a priori distributed as pi of kappa. We then do an experiment. We gather some data, yi, which is going to be some representation of the unknown function u of x. So in the temperature example, u of x would be the temperature. So maybe we would put some measurements. So we maybe take some thermal images and we would have measurements at certain points in the domain. These would be yi. And of course there would be error associated with those, measurement error. And then we just turn the Bayesian crank and say, well, what is the what is the posterior distribution of kappa given the measurements we've just made. Now, the thing is, of course, that this assumes that we have perfect knowledge of the solution of the forward problem, so u of x. And what we want to do here is we want to account for the fact that we've got an inaccurate forward solver in the inverse problem. So this is the notion of propagating uncertainty through subsequent computations. And why do we want to do this? You're going to see this example again in a very simple form. But in essence, if kappa is just a scalar value, and we obtain some data, we get the posterior. If we use a numerical solver and ignore the fact that we have uncertainty in the solution of u of x, and we plug that into our Bayesian machine and obtain our posterior, then this is what we get. So for a particular discretization of the domain, so where n in our expansion of our approximate solution, we get a posterior that looks like this. So it's biased, but as the level of discretization gets higher, so as the mesh becomes more refined, as we add more basis functions to our approximation, then what you see is that the bias reduces, and we then start to converge onto the value of kappa, I've said theta here, that actually generated the true value of kappa. Can anyone see a problem with this plot? If you were a statistician, is there a problem with this? Or does that look okay because it's converging? What's the problem with that distribution? The problem is that this posterior distribution here is biased, and its confidence is very high in the biased value. The variance doesn't indicate that in actual fact it's biased. What we would be much more happy with would be a posterior where its variance was much broader and therefore, you know, was less sure of its wrong mean value. So this is a case of overconfidence. Yeah? No. Okay, that's a good question. So the question is, this graph, these distributions, do not account for any uncertainty in the solution of the PDE, so why does it have non-zero variance? And the reason is because this is a posterior distribution that is conditioned on data, which itself has uncertainty. So the uncertainty in this case is driven purely by the uncertainty in the data. If, on the other hand, we take a probabilistic numerics perspective and we account for the uncertainty in the solution of the PDE, and we propagate that, then we get something which we see on the left-hand side. And here now you can see for the very coarse grid, we have a posterior distribution for kappa, which is much broader and really accounts for the fact that there is a lot of uncertainty associated with the the approximate solution because we've done a very bad job of modeling the function itself. But that approximation gets better and better as the level of discretization, so the number of basis functions increases. So this is consistent. This is, and unbiased. This is biased. It's consistent, but it's biased. So that's why we want to do it. Right? An inaccurate forward solver, in some cases, for an inverse problem, can produce biased and overconfident posteriors. So we want to do it. So in the last 9 minutes, I'm going to try and get through the way that we would solve the forward problem. And the way that we do it is, in a probabilistic way, is like this. So the elliptic operator, so divergence of kappa of x, grad u of x, I'm just going to write all of that as calligraphic A. Right? Just make everything shorthand. Because in essence, this is just nothing more than a linear operator acting on u of x. So I'm just going to sweep all this up into calligraphic A. So A is just going to act on our function u of x is equal to g of x. So we're now going to do a probabilistic solution for u of x. So this time, we now place our prior measure on the unknown function, which in this case is u, and we follow Larkin, and we define the probability measure in the Hilbert space of the solution functions of u, and we define it as Gaussian measure. And in finite dimensions, it will be a Gaussian process. We then observe data, and the data is basically just going to be a finite number of evaluations of the right-hand side, so g of x. So we're going to take a number of values of g of x, and that is going to be our data. And given our data, given g of x, we can then transform the prior on u into a posterior on u, given the evaluations of the right-hand side. Okay? That seemed fairly simple. Now, I had assumed that you had been given all of the Gaussian process lectures, and so you would recognize these equations. I'm sure some of you will. But if we have a Gaussian process prior on u, right, which we denote by gp, and I'm saying that the function, the mean function is 0, that may not be realistic. We may know what the sort of mean characteristic function might be, but just for this example, let's just set it at 0, and the covariance function associated with this Gaussian process is going to be represented by k. Now, alpha, the elliptic PDE operator, is linear, and under linear operators, Gaussian measures are closed. What does that mean? It means that if you have a Gaussian measure on u, and you apply a linear operator to u, then the distribution associated with the operator acting on u will itself be Gaussian. And so it turns out that given this Gaussian process prior on u, then the solution, the probabilistic numeric solution of that elliptic PDE, the forward solution, is basically going to be this Gaussian measure here. So this is pi of u given g. And it is a Gaussian process with a mean function m1 and a covariance function, sigma 1. And what's interesting is that the mean function at a particular point in the domain X. Now, when I talk about a particular point, let me just emphasize. So if I have taken a discrete grid here, then each of these nodal points would be, a value where we would compute g of x. And it turns out that the mean at that point x is just equal to this thing here. So we have the adjoint of the elliptic operator acting on the kernel function, right, which is computed at our inquiry point x, and all of the points where g of x has been evaluated in the domain. And so this is a vector, finite dimensional vector, and then we have the inverse of the adjoint and the elliptic operator, the PDE operator, acting on the covariance function of the Gaussian process for all pairwise points that have been probed. And so this is going to be a matrix which is going to be inverted, and then this vector G is basically the vector of all of the values of the G function that have been probed in the domain. And this is a classic GP linear regression solution. Now, it turns out that the mean value also happens to be the numerical solution for the PDE if you use what's called the symmetric collocation method. So that's kind of nice that our probabilistic numerical method in the mean is consistent with a standard numerical method for solving PDEs. But what we also get now is the covariance or the uncertainty associated with our solution given by this posterior covariance function here. And this is really quite nice. So what we've done is we've moved away from providing a solution, a numerical solution, which would be the mean, plus some estimated bounds on what the numerical error would be, and we've replaced those by a covariance structure associated with the structure of the actual problem that we're trying to solve. And just in case some of you are worrying about theory, there is theory here which basically tells us that the posterior over this particular function given g contracts to a Dirac on the true solution of the PDE at a rate that is governed by basically the mesh size, the order of the PDE, the smoothness of the Gaussian process prior, and the dimensionality of the domain. So we know that this is a consistent statistical construction. Now let me just, in the last minute, give you an illustration. So the example that I gave you was quite generic. Here is the same example, but just in one dimension, and kappa is just equal to 1, and we know what it is. So our PDE just is simplified to the second derivative of u of x is equal to g of x on the unit line, and at the leading and the trailing edge of the unit line, the function value has a value of 0. We define our prior measure on the solution as this Gaussian process, and the well, the function, the operator is just the second derivative. The adjoint is just going to be the second derivative on the other coordinate appearing in the covariance operator. We turn the handle to get this solution here. And if g of x is equal to sine 2 pi of x, then here is our probabilistic numerical solution for the PDE. Now, what you see is the little dotted line in the middle is the true solution, because we can get the analytic, we can get an analytic solution for this. There's the analytic solution. The mean value of our Gaussian measure is the bold line in the middle. And then the covariance structure, or the variance at each of the points, is represented by the shaded area there. So that tells us how uncertain we are. And because we've got a probability measure, we can draw sample realizations, right? Random function draws from that posterior that are consistent with the system of equations, with the data that we have gathered, and the animation shows random draws from the posterior. So this is quite a different type of solution to the classical numerical one, where you would be given, a point estimate plus some approximations of bounds on what the error happens to be. Here we now have a full probabilistic description of what the solution and the solution uncertainty happens to be. And we can therefore now propagate that uncertainty through any subsequent computations. In presenting to somebody, we can now very easily communicate the whole notion of uncertainty. And this is just a nice visual example. And then just to close for the evening, let's assume that we knew what the truth was, and we could work out what the actual error was from the truth as the number of basis functions increases. So you can see that it decreases at a given rate of order h, something or other. If we take the trace of the posterior covariance as our measure of uncertainty and error, and uncertainty associated with the numerical error, we can see a similar drop, right, in the uncertainty. And so this gives us a good indication that the probabilistic description is consistent with the standard numerical description, and the analysis that we've done shows that the rate of convergence again is consistent. So I'm going to close with this. So we've now constructed a probabilistic partial differential equation solver, a very simple one. And what I'm going to do tomorrow is now show how we can propagate that uncertainty in the next level of computation, which would be in solving the inverse problem. And then I'm going to go into some other stuff as well. Any questions in closing? Yes? What slide? So it's it's the boundary conditions plus these points here. 0.1, 0.2, 0.3, 0.4. Sorry? Yes. Yes, so that's a very good question, and one that you should ask whoever's talking about GPs tomorrow. So in the definition here, I have said that the prior for U is a GP, and it has got a covariance function K. Now, K typically would have some parameters associated with it, and those parameters will define the, well, they actually define the Sobolev space that we would be drawing functions from. And the way that we would select those values is by basically working out what the marginal likelihood is, and then either using Markov chain Monte Carlo to sample those, or to get a maximum a posteriori estimate of them. But, I mean, this is one of the issues, because although it's easy to say we're going to use a Gaussian process, what we're basically saying is we're going to define the function space that we're interested in via this covariance function. And that's not a straightforward thing to do. Yes? Yes, that's exactly what it is. Yes. That's right. So, yes. So, so that's a very good point, and it's one that we should probably discuss later in terms of the conditioning of this matrix here. I would call that an irritating practical problem rather than a grand conceptual problem. But it's a very important one because, yeah. Okay, I think you're all, I don't know what's next, but I'm going to stop before I get thrown out.